Hello, now we are going to look at how to do some cubic and exponential function problem solving. So where we have cubic and exponential functions in a story type context. So our first story is about cubic functions and it's about a race car training at a track. So the speed of our race car is given by v for velocity, is given by a cubic equation here. The speed is noted every second for the first 7 seconds. Now we can find the points that we would want to graph using our calculator, but it's also important that we know how to use our table. So if we're going to graph this for the first 7 seconds, we have our what's the car doing, what's its speed when we start out, when t is 0, up to 7 seconds. So we would sub in our values for t in our first column. The output of our function is going to be the speed or the velocity, and then we have our coordinates that we're going to graph, where t is the x coordinate and v or the speed is the y coordinate. So we have speed on the y-axis and we have time on the x-axis. So we'd sub in our value for time to begin with. We'd have v of 0, or speed at time is 0. It would be 0 cubed minus 10 times 0 squared plus 25 on 0. All of them are multiplied by 0, so that's just 0. So at time is 0, the speed is 0. And we'd fill in the rest of the table. When we filled in our table, we have all of our points, our t and our speed, our time and our speed. So we start off, we can see here the time coordinates are just going across in ones, but because this last number is very big, and some of the numbers in between are quite big, we've had to count on the y-axis in twos. And we need to be careful of that with these kind of real-world problems, because the numbers don't end up as nice when we try to bring in real-world things as they can be when we're just picking maths questions. So we have to be careful, what do our boxes count up in and to the side in, because that can catch us out when we are doing our questions. But here we start out at 0, 0, so we start at the origin always, and we start at 0, 0, then we start at the origin, go in the door 1, up the stairs 16, in the door 2, up the stairs 18, and we fill in the rest of our points. Now we need to see how to connect these dots, and to do that we need to know the general shape of a cubic function. So a cubic function, a positive cubic function anyway, will start by going up and then drop down and then go up again. And we need to know that that's its general behavior so that we know how to connect the dots properly. So we're going to do that now. So approximately this is the shape of our curve when we connect the dots, knowing that we should be going in a curve up and then down and then up again. Now we can use our curve now, our graph, to answer some questions. So what is the initial speed of the car? Initial is one of these key phrases that we need to know. It means when the time is 0. So when we start is the initial situation. So initially we know that our speed is 0. So we got that immediately. Time is 0, speed is 0. So that means that our initial speed is just 0. So v of 0 would just be 0. So our speed is initially just 0. Now what is happening to the car at 5 seconds? So we go to our time axis and we say we're at 5 seconds, so we're at this point here. What's happening at that point? Well, the speed is 0. So that means for a moment the car isn't moving. The car is stopped for a moment. So what does the slope of our line mean, or the slope of our curve I should say mean? Well, if we think about what's happening, this is giving us the speed of the car as time changes. So that's what's actually graphed here. If we think about what the slope gives us, it gives us the rate of change. How quickly is something changes is what the slope of something means. So if we think about the slope of this curve here at different points, it's how quickly the speed is changing. Well, our name for how quickly speed changes is acceleration. So the slope of this curve would give us the acceleration of the car at different times. what is the speed of the car at 3.5 seconds? So we go to our time axis and we want to know when the x value, the time value, is 3.5, what is our speed going to be? So we're talking about there. So that's time is 3.5, and then what would be the speed coordinate of that? We'd go straight across, and that's about 7 meters per second. About 7 meters per second. And we get that, and reading it off of the graph, we would make sure to mark our graph to show that that is how we are getting our information, that we're getting the coordinates of that point there. When the time is 3.5, the speed, or the y coordinate, would be about 7 meters per second. When is the car going at 12 meters per second? So this time we know the speed, so we know the height that we are. So we go across 12 and say, well, when is that happening? Well, that happens at this point here, it happens at this point here, and it happens at this point here. That's when the speed is 12. So what would be the x coordinate of that? If we drop down, each one of those is going in 0.2s, so that is approximately 0.6. So that happens at about 0.6. T is equal to 0.6 seconds. And this one is actually an exact point. That happens at 3. It's actually one of the points that we got, so it happens at 3 seconds. We mark that in on our graph as well, so we use our marks on our graph to show that we read this from the graph. And then where does that happen? If we drop down straight along, that happens at about 6.6 seconds. So we're showing with our little dashes that we know that we are getting this from the graph. Now, that is how we can solve problems with our cubic equations. We can also work with exponential equations. So if we have bacteria, they replicate, they reproduce very quickly, and their population is given by, the population P is given by 6 times 2 to the power of 0.5 t, where t is measured in days. So the fact that our input variable, t, is up in the power here is what tells us that we have an exponential type equation. So the power is often called the exponent, and that's where we get exponential. So the fact that our input variable is up in the power is what makes this an exponential equation. So what we're going to do is graph the population over the first 5 days. So just like with the cubic, we can fill in our population at different times. So we could say the population when t is 0, the initial population, would be 6 on 2 to the 0.5 times 0, and we would put that into our calculator, or so we would work that out, and it ends up being 6, because it ends up as 2 to the power of 0, which is 1 times 6, which is 6. So you end up with 0, 6. We can fill in the rest of our table. And when we've filled all of that in, we have our points. I've rounded some of these that were fairly close to whole numbers just to the nearest whole number. 8.5 or 8.48 was not particularly close to a whole number, so I left it as 8.5. But we do have to do some rounding in practice for doing our graphing. We can also get these values by creating a table in our calculator. But we're going to have our time value on the x-axis, and we're going to have our population on the y-axis. So that's what we have labeled here. So we are going to plot our points. So we start at the origin always, and we go in the door 0, up the stairs 6. And we have to be careful here, because these numbers get very big, we've had to scale our y-axis quite a bit. And we also have our x-axis spread out quite a bit here. So we need to be careful of how our numbers are going to work. So we have 0, 6. Well, we appear to be going up in 2's per box here. So 4, 6, 8. So that would be my first point there. And I fill in all of my points along. Now we've gone in the door and up the stairs for each of our points. We need to know that the general shape of a positive exponential is going to be something that it sweeps upwards like this. So we're going to use that knowledge to connect our dots. Now we have drawn in our curve. Again, we cannot use a ruler for this. It is a curve and we have to make sure that we do it freehand and as neatly as possible as a curve and not connecting the dots with a ruler because it's not a straight line. Now, what was the starting population? So how many bacteria did we have to start with? Well, starting would mean that time is 0. So how many bacteria did we start with? We started with 6 of them. The population was 6 when time was 0. What is the population after 1.5 days or 1.5 days? Well, we would go, okay, we want to be on our curve. So we want to be on our curve and we want the days to be 1.5. So we have to be careful about the way our boxes are working here. Our boxes here are going in 0.5. So 1 to 1.5 to 2. So we're interested in the time value being 1.5. We go up to our curve. We want to know what height we're at, what population we're at that time. So we go across and we know we're counting in 2's per box here. So 8 to 10 to 12. So there were 10 in the population after 1.5 days. The population at 1.5, this is function notation, would be 10. When is the population 20? So we want the time, we know the population. So we're going to go and say the population is 20. So when are we at that height? When are we at that population? That's happening there. And the x-coordinate, the time coordinate there, is halfway between 3 and 4. So it's one box over. It's going to be 3.5 days. So our time is going to be 3.5 days. So that's how we can do some problem solving with our cubic and exponential functions, and that is what we need for now.